Hello again. Let's do another video on chapter 5. Hopefully we can finish it in maybe two videos. I hope you're doing well. So let's get started. Let us get started here. So we are going to talk about substitution. So what is substitution? Let me quickly review this. We know, for example, that if we take the antiderivative of x to n dx, we know the answer is x to n plus 1 over n plus 1 and then plus some constant. Now the question is, what if so this structure works, and in fact this structure actually looks like this. If we have, of course, can't have happy face, but let's say we have happy face to the nth power, and then this part of it is also d of happy face. If that is true, the answer to this also is happy face to the n plus 1 over n plus 1 plus c. So this structure works if we have these parts in it. For example, we have something to the nth power and d of something. So this d of something and this base here have to be the same. That is true for all the formulas in the table of integrals. That is also true. So the question is, of course, normally in textbooks, we always have dx here. We don't have d happy face or d something else, but we can make it that. So that's the idea of substitution, to make structures that don't look like the structures in the table of integrals look like the structures in the table of integrals, so we can integrate them. Okay, so that's the idea. So here's an example. Let's say we have x squared plus 3 to the 10th power, right? And then we have 2x dx here, right? Now, it does not look like that, obviously, right? It doesn't look like that. It's not x, it's x squared plus 3. But can we make it look like that? And the answer is yes. So this section actually is called U substitution. And the U is like the happy face we use. Instead of happy face, we use U. So we're going to make this U. So let U be x squared plus 3. And then we know that du dx, which is the derivative of this with respect to x, is 2x. Now, if we want to change this structure, we have to write everything in terms of u. So this becomes, this is u to the 10th power. Well, that's promising because that looks like this, right? And then this part of it, the 2x part, I can't do anything about. I have to write it. But the dx here, I'm going to find what dx is supposed to be equal to in terms of u. So here, I'm going to solve for dx. And if you solve for dx, obviously, if you cross multiply, dx is going to equal to dx times 2x is du, right? So dx is du divided by 2x, right? So instead of dx here, I'm going to put du divided by 2x, and notice that somehow magically we get this structure. Well, of course, it's not magic, it's math. And this is structure now, clear that one. This structure looks exactly like that. Something to the nth power, d of something, right? In the textbooks, you usually don't write that in this form. They should, but they don't. But so we're not going to do it this way. We're going to do it this way. We're going to use U substitution. So we're going to make whatever we like to be U, U, and then hopefully this structure simplifies into something we can integrate. So now we're going to integrate with respect to U here, and we know what to do. The answer is U to 10 plus 1, which is 11, divided by 11 plus C. But we know what U is. U is this, right? See that? So this answer would be x to the second power plus 3 to the 11th power divided by 11 plus C. That's the answer. Now, another way to do that, of course, would be to expand this and then do it separately, which is a big algebra mess right there, right? So that's the idea of substitution. Officially, this is how it is given in textbooks. So you see, this is f of something, and this is g prime dx is actually what? Is the derivative of that function right there, right? So in the example that I use, what was it? X squared plus 3. So in the example that I use, we had x squared plus 3 to the 10th power, right? And dx. So now, you see this structure says if you have f of g of x, so if you think of f of x here, f of something as, so we got f of something as something to the 10th power, right? That's the f of x. And the g of x part of it is this function. So f of g of x here is actually when you substitute x squared plus 3 here, right? So that's the structure that we have. And then this part of it, it's supposed to be what? It's supposed to be g prime dx. I didn't have dx, I had 2x dx, remember? That's why I put 2x dx here, because I knew that I wanted what? I wanted g prime to be here. And notice that the prime of this is 2x, right? So that's what it is given officially. But instead of g, we just use u. And we're going to call it u substitution. So this is u prime, right? So if this is u, then this is g prime is actually du dx, right? And then dx gets canceled, so we just get f of u du, right? Which is that right there. And then we know how to integrate that if we have formulas, right? All right, so let's look at some examples. Here's an example. So to do this, first you have to go to the table and see which formula in the table of integrals kind of we have to use to do this. It looks like something to the 4th power. So that's a clue that we have to think of u to n du, right? So if we make this u to the 4th power, can we simplify it to this form? And the answer is yes. So let u be this, and then du dx would be 6x, and then dx would be du over 6x, right? So we are going to substitute that for dx, and we're going to substitute u for that. This is what we're going to end up with. And of course, we have 6x here. We can't do anything about that. We have to leave it there. Hopefully, the variable part of it gets canceled. And in this case, it does. In fact, the whole thing gets canceled. And we have what we wanted. Now, we know how to do that because we have a formula for that. Right? Over n plus 1 plus c. So the answer is u to the 5th over 5 plus c. Now, what is u, of course? U is that. Then we substitute for it, and we have an answer. Okay, so that's this process is called u substitution. And it's important to go through the steps here. Substitute for dx and for whatever you set equal to u. and then cross your fingers, see if things get canceled and we got what we wanted. Now obviously, if I had 3x to the second here, it would not work, right? And that's why we have calculus 2. In calculus 2, the first thing we want to do is to talk about the structures that we couldn't integrate in calculus 1. All right, so there is more to it, but we're going to continue in calculus 2. So here's another example. Again, this looks like, if we assume this is u, this looks like the square root of u. Now, square root of u is good because square root of u is u to 1/2, and again, is the same structure, right? U to the nth du. So this is the direction we want to go. So we let u be z squared minus 5, and let du, of course, if the u is this, du is 2z dz, right? And dz is du over 2z. So we're going to take this, substitute for dz, and put a u here, and hopefully that z gets canceled, and it does. So this would be z square root of u, and then dz is du over 2z, and then the z's go away, but there is a 2 left over in the denominator. That's okay, we can move it out of the integral, because we know constants don't matter, we can move them out of the integral. So it would be, think of a 1 here, so 1/2 comes out. And this structure is good because it looks like that. It's just the power is 1/2. This is the same as u to 1/2. And the answer would be u to 1/2, first of all. We can't do anything about that. We have to keep it. And this would be u to 1/2 plus 1 divided by 1/2 plus 1. 1/2 plus 1 is 3/2. And then dividing by 3/2 is the same as multiplying by 2/3, right? So this is the answer. This would be 1/3 u to 3/2 plus c. Now u, of course, is z squared minus 5. So that's 1/3 z squared minus 5 to 3/2 plus c. And then 3/2, of course, the power, a to m over n is the nth root of a to m, right? So that's the second root. So that is the second root of inside the stuff to the third power, right? All right, so that's the answer. Find the integral. Again, what the structure does it have? It looks like something to the 10th power. So again, we go with this. And in this case, our u is sine theta, and we go from there. So let the u be sine theta, and then du d theta would be cosine, because derivative of sine is cosine. And here we're going to isolate d theta, because we have to substitute this for it. So du over cosine theta goes for d theta. Cosine theta is u. Cosine theta we can't do anything about, we have to leave it. And then sine is u. So it's sine, so it's u to the 10th power. Notice that this is the same as sine of theta to the 10th power, right? That is the same as that. So u to the 10th power, cosine we have to keep, and then du over cosine. And you see, it gets canceled and we get the structure we wanted, right? Exactly like that. So the answer is u to 11 over 11 plus c, and we know what u is sine. So the answer is sine to 11 over 11 plus c. Okay, that's the idea. Now again, this method doesn't, in fact, most of the times, this is not going to work. That's why we have calculus 2. But for now, even in calculus 2, we have to use u substitution to simplify structures. So you got to learn this. Okay, here's another one. Now here, what happens if the integral is actually a definite integral? Well, when we write, let's say, f of x dx, right? these are actually values of x. We don't write them, but if you write a to b, these are actually x values. Now, if you do the integral in terms of, let's say, u, then these values here, the two limits of the integral symbol, would be in terms of u, let's say c and d, right? So when you convert to u, you have two choices. You can do the integral with respect to u. So whatever your u is, you have to find out when x is a, what is u, and when x is b, what is u, and then find a definite integral. So in this case, and it's usually easier to do it in terms of u than going back and doing it in terms of x. So let's look at this example here. First of all, this looks like some structure, like something to a power, but isn't the denominator, but that's okay, because we can bring it to the numerator and make the power negative, right? So let cosine be u. So that would be u squared here, and then what's the derivative of cosine? Is negative sine. And from here, let me erase all that. So from here, we're going to find out what dx is. And this is going to be substituted for that. Now we know this is u squared, and this is sine x, right? Now this is good, but remember, we have to change the limits too, because these are in terms of x, right? So the question is, when x is 0, what is u? Well, we know u is cosine x, so when x is 0, u is cosine 0, which is 1. And when x is pi over 4, what is u? Well, u is cosine pi over 4 because it's the square root of 2 over 2. So this structure turns into this structure where we substitute u for cosine, we keep the sine because there's nothing to substitute for, and then dx is this structure here. And also we change the limits. When x is 0, u is 1. When x is pi over 4, u is the square root of 2 over 2. And so everything cancels except there is a negative here. We have to bring it out and put it outside. And we get this, which is actually what? Which is this, right? U to negative 2. Now, remember when we do definite integral, a is always smaller than b. What if a is bigger than b? Well, we can what? We can switch them. Just put a negative before it and make it b to a, right? So we can make it b to a, as long as you put a negative before it. So here, obviously, square root of 2 is like, over 2 is like 0.7 something. We can't do from 1 to 0.7. We have to bring the 0.7 here and put the 1 there. But to do that, we have to multiply by negative, and there is already a negative here. So negative times negative would be positive. So this integral is the same as integral of square root 2 over 2 to 1, u to negative 2, du. And we know that integral of u to negative 2 du is u to negative 2 plus 1 over negative 2 plus 1 plus c. Now negative 2 plus 1 is negative 1, and that's negative 1. So basically the answer to this is negative u to negative 1 plus c. But since this is a definite integral, we don't use the c. We just use that, and we are going to evaluate it from a square root of 2 over 2 to 1. So first we have to put the 1 there, right? 1 to square negative 1 is 1 over 1, which is 1, and there's a negative here. Minus negative, so it would be, let me write it up here. So it would be negative 1 to negative 1 minus negative square root of 2 over 2 to negative 1, right? That's what it is. Now this, this negative this to negative 1 basically means reciprocal of this. So it would be a negative, that's just 1 over 1. Maybe I shouldn't explain all this, you already know, but I do it anyway. So that would be negative 2 over the square root of 2, right? Because we have to take the reciprocal. And a negative and negative would be positive, so that's negative 1 plus 2 over the square root of 2, which is approximately that. That's the answer. Okay? So that's how we deal with definite integrals. It's better to do it in terms of u. All right, substitution with definite integral, we already talked about this. These are x's, x values. And then if you assume that there is a function in here, then when you convert in terms of g of x, then these would be g of a, and that would be g of b, right? G, of course, is our u. All right, so use a suitable change of variable to determine the indefinite integral here. Okay, again, there is a structure, looks like something to a power, but we've got a bunch of stuff here, extras. Hopefully we can get rid of them. Okay, let u be cosine t to the third. So if that's the case, if u is cosine t to the third power, then derivative of cosine is negative sine of something, right? Derivative of cosine something is negative sine something times derivative of something inside. So that's 3t squared dt. From here, if you solve for dt, you basically have to take all of that and divide du by that. So this is our dt. That goes for dt. And of course, this part of it is u. So we get u squared. T squared stays because we have nothing to solve for it. Sine t to the third stays. Dt becomes du over all that. And what happens? Well, they get canceled. See, these two get canceled. And then there's a negative left here. And then t squared gets canceled. But there is a negative 3 left over. We have to bring it out, right? And it's in the denominator, so we have to put negative 1/3. And then what's left in integrand is just u squared du. And the answer to this is we keep the negative 1/3, would be u to the third over 3 plus c. But what is u? Well, remember u is that. So we put u there. And we could take this 3 multiplied by 3, get 9. So that is the answer to that u substitution. Here's another one. Can we do anything with that? And the answer is yes. You do a few of these, you kind of look at it and see, okay, this is u substitution, I can do it. Right? If you think of this as something is squared, do we have the derivative? The variable part of the derivative that we can cancel? Yes. So let u be x to the third minus 3, right? Then du is 3x squared dx, so dx is du over 3x squared. And notice that it's not exactly x squared, but it's 3x squared, but that's okay. As long as the variable part gets canceled, is good. Because numbers, we can take them out, that's cool. That's not a problem. So this structure turns into, this is u squared, this we keep, dx is that, the x squared part gets canceled, 1/3 comes out, right? And inside we end up with just 1 over u squared du, which is basically, again, u to negative 2 du. And we know how to do that. We keep the 1/3 and then u to negative 2 plus 1 over negative 2 plus 1. We just did one of these. Plus c. And then, you can do some simplifying, move that u to the denominator, right? Put that negative before the fraction. And we know what u was, so that's the answer. Okay? All right. Here is another one. Evaluate this. So we're going to evaluate this with some constant c. But remember, I talked about in the previous video the connection between the definite integral and indefinite integral. And we talked about the fact that this number here determines the constant. So the question here is, first find the antiderivative of this, then use this structure and find out what should C be in order for this to equal to f of x plus c, where f of x is the antiderivative. Okay, so let's talk about this first. How do we do this? Well, this looks like if u is right here, then u equals to x squared plus x minus 6. du is 2x plus 1 dx, and dx is du over 2x plus 1. So that's our dx, right? All right, if we write this as this we keep, that would be e to u, and then dx is du over 2x plus 1. 2x plus 1 goes away. That's just integral of du, e to u du. Now we know the derivative of e to something. We know the derivative of e to x is e to x. So integral of e to x is just e to x. And that's something we could do in the next section. We're going to work more with exponential and logarithmic. But for now, we know this is simple. Integral of e to x is e to x. Integral of e to x dx is e to x. And integral of e to u du is e to u, right? All right, so integral is here. Basically, this is the same as this. So the answer is e to u plus c, and our u was that. So the answer is this. So that part right here is our what? Our capital F of x here, right? And then plus some c. Now the second part of this is, what if we want this to equal to, so this is a specific member of this family. What member is that this equals to? And to do that, we're going to take, we know how to do this. We know that integral of f of x dx from a to b is capital F of b. Capital F is antiderivative of this, minus capital F of a. Now instead of a and b here, we have -3, and we have what? We have x. And instead of f of x, of course, we have all that. But we could do that. So antiderivative of all this, we just figure out what that is, right? This is right here. So the answer to this would be this function, if you evaluate it at x, minus this function if you evaluate it at -3. So it would be, if I put an x here, it just would be the same thing, right? It's the same thing. So e to x squared plus x minus 6 would be that. And then if I put -3 for x, it would be -3 squared minus 3 minus 6. And all of this, of course, is 0. That's 9 minus 9 is 0. So this is basically e to 0, right? So on the left, we want to, so this is the answer, right? So that's the answer. We want this to be equal to what? To f of x plus c. But this is f of x is the same. F of x is just that. So that means our c has to equal to this. This is our c. And what is that? Is negative e to 0, which is -1. So our c is -1. So this structure gives a specific family, member of this family of functions. And that specific member is the one that has c equal to -1, right? All right. So I'm going to do another video for the rest of this chapter 5, okay? So let me go back and see if we can Where are we? Here you go. So take care of yourself and others, and I see you in the next video.